All right, so we're going to go ahead and finish this off here by looking at how to compute the backpropagation portion if we're looking at a hidden layer node. In this case, I want to take the derivative of the error with respect to the weight from I to j, where I'm referring to that network diagram from the first video, where capital I is an input layer and capital J, this is the part that matters, is a hidden layer. Okay. Now the error is just the error. That's the equation we wrote down the first time. 1/2 the sum across all the output nodes of the difference between the output and the target value, quantity squared. One important thing to note here, when we take this derivative, the weight from I to j has nothing to do with the subscript k, not directly. So this sum certainly we can't drop immediately because, in fact, the output from node j is going to be output to every single node in layer k. So I would actually expect, realistically, that this sum needs to stick around. So let's go ahead and compute this derivative here. Similarly, we're going to use power rule, bring this 2 down, and then the chain rule, right, to compute the derivative of the inside. I'm free to pass this derivative inside the sum. It's finite, and that's not a problem. And we end up with this, right, the sum across all the output nodes. This is left over from the power rule times the derivative with respect to the weight from I to j of the inside. The inside being output of k minus target value of k. Tk is a constant, so that's going to disappear immediately. And this is the only expression that really matters, right? Now let's go ahead and compute this. Remember that the output of k is actually going to be quite easy to compute because it's really just sigma of the input of k. Now sigma is our sigmoid transfer function. It's very easy to do this because we already know the derivative. We did the work first. And so we will go ahead by the chain rule, get sigma of input times 1 minus sigma of input, right, as the derivative of sigma, all multiplied by the derivative of the input with respect to the weight from I to j, which we're concerned with. Now what we're going to do is exactly the same as for the output layer nodes. Notice that sigma of the input is just the output of the kth node. 1 minus sigma of the input of the kth node to the kth node is the output of the kth node. So these two terms right here, just like before, are going to turn into script O sub k times 1 minus script O sub k. This term, the derivative of x sub k with respect to the weight from I to j, I particularly dislike. This I'm trying to take a derivative of something with subscript k as it changes based on subscripts I and j, neither of which are the same. And so what I'm going to do is break this apart by the chain rule. How I'm going to do it is to note that the input to node k is going to depend on the output from node j, and the output from node j is going to depend on the weight from I to j. So let's go ahead and rewrite this using the chain rule to break that apart, and these two terms, we'll just rewrite these as output of k, right? Like this. Here's our output of k, 1 minus output of k. And I've broken down the derivative that we were talking about before into dxk with respect to script O sub j times derivative of O sub j with respect to the weight from I to j. Right? By the chain rule, this is totally legal. The other thing that's nice to note is now this is real easy. The input to the kth node with respect to the output of the jth node is really just the product of the output of the jth node times the weight from j to k, right? So when I compute this derivative right here, I get just the weight from j to k. That's nice. Another thing that's nice is this last derivative term here now no longer involves the subscript small k, so I'm in fact free to take this outside the sum, like this, and I can work with it up here. This is essentially done. As a sneak peek, you'll notice this expression right here involving k is our delta sub k that we talked about before. And all we do is we take that delta sub k, multiply it by the weight that connects it to the previous layer. We add them all up, and we're going to move that forward, right? So this is why we defined that delta sub k. So that'll come up in a second. For now, let's go ahead and finish computing this derivative here, d O sub j with respect to the weight from I to j. This again is very straightforward, right? Script O is really sigma of the input. I know how to compute the derivative of sigma, which is again sigma times 1 minus sigma evaluated at the input, which I'm going to go ahead and skip that garbage step and turn it straight into this product, output of j times 1 minus output of j, times the derivative with respect to the weight from I to j of the input to j. And this is real easy to compute, and is in fact just the output of the ith node, because the input to the jth node is just the output of I times the weight from I to j. So when I compute this derivative, all I get is output of I. Okay? Now, like I said, we'll recall our definition of delta sub k. We will rewrite this expression here as delta sub k, which I do like this. All of that delta sub k times the weight from j to k stays inside the summand. We add all of those up. We multiply those by this, output of j times 1 minus output of j, which is really just the derivative of our transfer function, again times the output of the node we're concerned with of the previous layer. Okay? So to do something similar, what I'm going to do is now define everything besides the O sub I term to be delta sub j, which if we look back at the definition of delta sub k, I defined everything that involved k, which was everything except for the output sub j term, to be delta k. So if I define all of this here to be delta sub j, which is again just a function of delta k multiplied by the weights, which is a beautiful equation, we can rewrite this as dE dW sub ij is going to be the output of I times delta j, right? So let's go ahead and look at both of them. For an output layer where we have a node little k in cap k, the rate of change of error with respect to a connective weight connected to an output layer is just the output of the jth node times delta sub k, right? Where delta sub k is this expression. This expression really is just the derivative of the transfer function times the delta in the output and the target value that we actually desire. If the node that we're looking at is in a hidden layer, any hidden layer, what it's going to be is the output of the previous node times delta j, where delta j is going to be, again, this expression, which is really just the derivative of the transfer function, times the sum of all of the delta k's, where k is the next layer, times their weights that connect them to the node we're concerned with. Okay, add all those up, multiply it by the derivative here, that gives us our delta sub j, multiply that by the input that we're concerned with, and that gives us this quantity that represents how the weight that we're concerned with that connects node I and node j affects the error. So what about those bias terms, right? We need to incorporate the bias terms, which we called theta, into the equation to see how they affect errors too, right? Because they're part of it. You'll notice that the rate of change of the output with respect to the bias term is 1. Now, if you go back and plug all that stuff in, I'll go ahead and leave this to you. It's very trivial, but it turns out that this is just 1. And this is actually why a lot of people choose to view the bias term as an output from a node which is connected to the node we're concerned with, which always outputs just 1 all the time. And you're free to move this around as such. Okay. Also, if you go ahead and run through the previous procedure looking at this derivative, you'll you'll find that it holds for any layer, regardless of whether it's an output layer or a hidden layer. And this is going to go ahead and be because the output of the layer is replacing the output from the quote-unquote previous layer. Okay. And so you'll see that the rate of change of error with respect to theta, which is what we're concerned with, ends up being exactly just delta sub L, right? Where L is whatever layer you're looking at. And this is for all layers, so you're totally free to do it. And this is because, let's go back here, what we're doing is, if we redid all of this work and instead we're concerned with the bias terms, all of this junk that gives us these deltas would go exactly the same, except this output that we're thinking of doesn't exist. That's not I mean that we're not, it's not connected to anything. And so when you take the derivative here, you get precisely 1, right? Which you can do, it's very straightforward. So, how do we actually do the backpropagation algorithm? What you're going to do is, given your set of input data, you're going to run the network forward to get the actual output from the network. For each output node, we'll call them little k, you're going to compute this delta k value, which we talked about before. The output of k, which you have right here, you know because you just ran the network forward. The value t sub k you're supposed to know because you're training it to fit this data, so you compute this expression. Okay. For each hidden node, you're going to calculate this expression. Given this delta k that I just computed for the output layer, I'm going to multiply that by the connective weight from j to k. I'm going to add those all up, multiply them by this expression, right, which is the derivative of the output of the jth layer, which you're going to have to hold on to, right? So when we develop our C# class that does this, we're going to actually need to kind of keep tabs on what the output was at every layer in the process so that I can compute these delta j's for all of the hidden layers. And I will use these delta k, delta j's, etc. to go ahead and update those values. And so you'll see that we hold on to those. Okay. So now that you've computed these, again, this is for an arbitrary hidden layer. I've only shown you one, but the expression is exactly the same, where the delta is, in this case, the delta of the hidden layer downstream. So then you're going to update the weights as follows. Negative eta, right? Eta is just going to be a small number, maybe whatever, 0.1, 0.2, which sort of scales down the delta that we're going to train by, times the delta that you're concerned with, times the output of the previous layer, right? The change in bias for a node is going to be eta, sorry, this should be negative eta right here, times that delta because there is no output of the previous node, it's just 1. Okay? We're going to compute these values, take whatever weight we currently have in the network, add this delta W, and replace it similarly with the bias terms. Okay? So that is basically it. My apologies for missing this negative right here. There should be a negative eta. The reason it's negative, I like to think of eta as a small positive constant. But the reason it's negative is because what we really just do is compute the gradient of the error with respect to all of these weights, which of course, as you all should know, points in the direction of steepest ascent. But what I would like to do is descend on this, whatever dimensional error surface. So I choose to move opposite to what we just computed by some small coefficient of essentially the derivative, right? Which is how this affects it. And that's it. So I hope that helps. Sometime soon I will put up a video which will help us develop a very flexible and usable C# library for neural networks. And you guys will be free to mess around with it and teach your computer to think, or whatever you want to do. So, alright guys, hopefully this is helpful, and I'll see you soon. Ciao.